I'm going to talk about a joint work with Jan Pulmann, Friedrich Valach, and Donald Youmans. And I apologize a bit in advance. This is going to be some kind of physicsy talk given by somebody who doesn't know anything about physics. So you're going to get like the best of both worlds. And the first part of the talk is some sort of picture for dualities in a quantum field theory. And the second part will be some calculation of some particular thing that is happening there. So what do I mean by those dualities? Let's start with some kind of simplest and very naive example of electromagnetic duality. So imagine that you have this kind of, sorry, I'll try to make it bigger, this kind of Maxwell type equations in vacuum, but where now F is in principle a form of an arbitrary degree. So we can either think of F as the important thing, and then we say that locally F is equal to D of A, and now declare that A is our actual field and write the axiom functional in terms of that, etc. Or we can decide that it's the Hodge dual of F, who is more important, and we write it as D of some A tilde, and do the same thing on this side. And we get somehow two pictures of this, basically the same thing. Now, if we do it slightly less naively, so the first dimension when something interesting can possibly happen is n equal to 2 when F and also star F are 1 forms, and therefore A and tilde A are 0 forms, functions. So then, if you want to do it somehow properly, actually also A tilde should go to the circle rather than to R, but it's not a big difference. And if we say set up the length of those two circles in the proper way so that the product is equal to 1, then we actually get an isomorphism of two-dimensional quantum field theories. These are free field theories, but still they are quite interesting, even though they're free. And this is what is called T-duality, this isomorphism. This is a reasonably easy generalization when instead of a circle we take a torus, and instead of the other circle we take its dual torus. It still works, and then it has some generalizations to more like torus bundles. But let me not talk too much about that. But there is a non-abelian version of this picture, of this T-duality, which is called Poisson-Lie T-duality. And you're somewhat less likely to know this because this was my childhood project, so the thing that we did with my PhD supervisor, Ricci, a long time ago. So what's happening there, that now we start with a Manin triple. And so there's some G with invariant pairing, and inside we have two Lagrangian Lie subalgebras, H and H tilde. And there's this similar picture of two quantum or possibly just classical field theories. So these are two-dimensional sigma models with target spaces equal to G mod H or G mod H tilde. And in this case, I cannot say that we get isomorphic quantum field theories. Such a statement is not known, but they are sort of almost isomorphic. And I will not tell you right now what this almost means, but they differ in some sense by some finite number of data. Or okay, let's see what happens in a moment. And also, I don't know how to present this non-abelian version in this super easy way, but well, that's life. That's what happens with non-abelian things. And then, of course, we can go away from dimension 2. So the most interesting, most natural thing would be to go to dimension 4, where we would get the ordinary electromagnetic duality. And somehow, since this Poisson-Lie T-duality was my childhood project, now it was also my childhood dream to find some picture that would contain non-abelian dualities in arbitrary dimensions. And this dream lay dormant for a long time. until somehow something happened recently. So yeah, that's the question. So what is the unified picture that would give also some non-abelian versions in higher dimensions that would know that these higher dimensional field theories are actually gauge theories and things like that? Okay, so the picture is, as promised, a sandwich. So what do? We're going to construct an n-dimensional quantum field theory, so on some n-dimensional sigma, let's say. And the way we do it is that we multiply sigma with a unit interval, and we also pick up a topological field theory, n+1 dimensional topological field theory, and we put it to this now n+1 dimensional manifold sigma times interval. But this has two boundary components, so we need to specify boundary conditions. And those two boundary conditions are going to be kind of different in nature. So one of them is going to be non-topological, or dynamical, so it will have some local degrees of freedom. So things are really happening here. This is like, I don't know, a boundary field theory. And on the other boundary component, on sigma times 1, we choose a topological boundary condition. So something like easy that has no, or easy, I don't know, something that has no local degrees of freedom. And now this picture altogether, somehow it lives, I can say it lives on sigma, so we can see it as a field theory, as a quantum field theory on sigma. And now the picture now says that, well, let's keep everything fixed. Just replace this L with some other L. Then we're going to get some closely related, but not quite the same quantum field theory on sigma. And this is the way how we're getting those mutually dual quantum field theories. So that's the picture. And what sometimes happens, but not always, that if you obtain it by quantization of some classical field theory. So it can happen that we have two classical boundary conditions that are classically different, but after quantization, they become equal. So this would be like a true duality in the sense that we now have non-trivial true isomorphism between two quantum field theories. But if it doesn't really happen, then we don't have to despair. It's still fine.
But excuse me, Paul, is this a statement or is something that you want to prove?
Right. So that's why I said it's a physicsy talk. This is like so what one can say. This might be set as a definition, but then there are examples that existed long before this definition, and so now the statement is that all those examples are particular cases of this thing, and that this picture somehow explains those examples and in a uniform way.
Thank you.
I don't know whether it makes sense. Okay, now let me come to one of those examples, which is that Poisson-Lie T-duality. So just to tell you what kind of topological field theory we should choose and what is going to be this dynamical boundary condition and what kind of topological boundary conditions one can use there to get it. So for Poisson-Lie T-duality, so that's for two-dimensional things, it's for two-dimensional sigma models. We need to take a three-dimensional topological field theory, which is just Chern-Simons theory. So here is this traditional action functional. I'm going to talk mostly about these things in the Battle and Wilkowicz formalism. So that's why this A, which is ordinarily a one form, is going to be really a form of an arbitrary degree with values in our Lie algebra. And yep, I remind you that for us, for this sandwich picture, this three-dimensional M, which is here, should be sigma times an interval, where sigma is a surface. And now, what kind of boundary conditions we're going to consider? So first, I'll tell you this topological boundary condition. So for that, we simply, in G, which is a Lie algebra with an invariant pairing, we pick up a Lagrangian Lie subalgebra. And then we restrict this A to B. When we restrict to sigma, we demanded that it has values in H. Maybe some little comment. Once I take forms of arbitrary degree and the fact that we have also omega 0, sigma, comma H, it means that we have gauss with values in H, and it corresponds to the fact that this boundary condition has still a gauge symmetry on the boundary, but now with values only in the group in the group H. So inside, in the bulk, gauge transformations can be arbitrary with values in G, but on the boundary, they can be only in H. And that other boundary condition, that non-topological or dynamical, it's some sort of little generalization of what is called chiral boundary condition. So what it requires a choice of a complex structure on sigma. So that's one thing. That's one way how to see that it's not topological anymore. And it also needs this strange data that we need to decompose G to orthogonal direct sum of two vector subspaces. And we should also require, it's a technical thing, that the pairing on G is positive definite on V plus and negative definite on V minus. That's what those signs stand for. And this is what is called a generalized metric in some community. And the boundary condition simply says that the one form part of our A is of this type, that okay, there is a form of type 1, 0 with values in V plus, and forms of type 0, 1 with values in V minus. There are no zero forms, which corresponds to the fact that there are no gauge transformations anymore. So this condition kills gauge transformation on the boundary on sigma. And corresponding to that, so to keep a Lagrangian sub thing, we have here this omega 2. Okay, anyway, so these are our two boundary conditions. One of them given by a Lagrangian subalgebra, the other one given by this kind of arbitrary looking data. And then, as I said, we should take now Chern-Simons theory on sigma times interval with one boundary condition and the other boundary condition. And the statement is that this is actually isomorphic to a two-dimensional sigma model where the source, the worksheet is sigma, and the target is G mod H. It's not supposed to be evident, but at least to get some idea where this G mod H comes from, it basically comes from taking holonomy of our connection along the vertical this vertical interval. But so that would give us a thing from element of G. But since we have still those gauge transformations with values in H on this green part, so it's defined, well defined only modulo H. So that's roughly how this happens. But yeah, it's not terribly clear why it is a two-dimensional sigma model, or for that matter, what is the metric on G mod H? The metric is that there is kind of, yeah, it's not obvious, it's not G invariant. It's a strange thing. So let me now explain you.
Is this isomorphism some kind of dimensional reduction, or?
Yes, in some sense, yes. But we'll see that just basically in a second. But yeah, you're right that we somehow there are how to say it. So we have somehow too many fields in some sense because they can depend arbitrarily on that I, but in the end we'll get rid of them. And the way how to understand how to get rid of them or what's really going on is that this the sandwich picture is can be explained in a slightly different language as a derived intersection of Lagrangian submanifolds. It's best visible when our topological field theory is of AKSZ type. So Chern-Simons theory is a particular example of that thing. So there are just some little preparatory remarks for it. this AKSZ theory. It's n+1 dimensional topological theory, and for that we need a differential graded symplectic manifold with symplectic form of degree n, or if you prefer, whatever is a higher derived stack or something, doesn't really matter. And the space of fields, if M is a n+1 dimensional manifold, it's this mapping space. So maps from T1 of M into X, which now has a symplectic form degree -1. So it's like a classical BV manifold. So it's one can say it gives us a solution of classical master equation. This would be okay if M is a closed manifold. But we now really want to consider the case when M is equal to sigma times I, where sigma is a n-dimensional thing, right? So then we also need to impose some boundary conditions to make everything right. But before doing that, let us just use this splitting of M into this product of sigma times I. So let's consider this mapping space from T1 just of just sigma to X. So what one can say is what one can call the space of boundary fields. So it's denoted by this fancy X. So it's a DG symplectic thing with the symplectic form of degree 0. And then this space of fields, we can say that, well, it's a kind of by definition is the space of maps from T1 of interval to X, or if you wish, those are paths, the path space of X. And we also need to somehow understand what those boundary conditions are. Well, since X, this fancy X is our space of boundary fields, a boundary condition is going to be simply a DG Lagrangian submanifold in this DG symplectic thingy. And now we can somehow understand slightly better or in a nicer way what this sandwich picture is. So remember, our fields are paths in X, but we have those two boundary conditions. So these are paths that have to start at the first boundary condition, let's say Lagrangian submanifold, and have to end at the other boundary condition. So in other words, what we can call it the homotopy or derived intersection of these two Lagrangian submanifolds of that fancy X. And now there is this kind of mantra in this shifted symplectic geometry, or maybe I should say it's a theorem, but which says that if you have two Lagrangian submanifolds and if we take their intersection, then this is a symplectic thing. Just the symplectic form has degree which is lowered by 1. So in our case, X has a symplectic form of degree 0. So that's why this derived intersection is going to have a symplectic form of degree -1. But we don't need to use this advanced language, because in this particular case, this symplectic form of degree -1 is this one, and simply given to us by the AKSZ construction. So differential comes from there. So everything is fine. But still, what we can do is that instead of taking that derived, computing the derived intersection of F with L in this, kind of universal, but also very big way where we take the space of all paths going connecting F and L. We can try to cook up some smaller resolution and see what happens. We should get the same or quasi-isomorphic result in the end. Yeah, so that's somehow what happens. So instead of taking this big resolution of L, so what is this big resolution? It's basically that we're taking all paths which are in X that start at L. So all those possible things that's going to give us some resolution of L. But if instead of that we take something smaller, in practice, this might mean that we take just straight paths, or maybe even straight paths that go in some particular directions that are transverse to L. Then we're going to get a quasi-isomorphic picture, and we're going to get our field theory on sigma. So what is happening in the case of the Chern-Simons sandwich? So there, this topological boundary condition that L, that's given by the Lagrangian Lisa algebra of G. Now, sort of minimal resolution of the thing looks like this, that we take homogeneous space G mod H times G1 to G1. So this is now a nice submersion. And now you can probably start believing me that if you plug in all those things into the formulas, what we get is in the end a Batalin-Wilkowski type of description of the sigma model with target G mod H. That G mod H really comes from here.
Pavol,
yeah. Mm-hmm.
Just a naive question. But a kind of less enlightened explanation would be if I just write down that action functional, then will it be true that like the variable, whatever, some combination of fields, whatever, some substitution would also give you an action functional on the boundary, or this is not that naive? I kind of, right, you explained from big principles how it goes, but is it also some down, can it be replaced by some down-to-earth calculation on the action functional, or not really?
Let's say I don't quite know. To some extent, sorry, it's horrible with this coronavirus. To some extent, one can do play such some tricks like. So I said that there are too many fields. I mean, this X is somehow way too big. So the tricks that one can play is to basically discover that some of those fields are Lagrange multipliers, and they impose some constraints and do such stuff. Just it worked perfectly well for this Poisson-Lie T-duality. But then maybe my collaborators would know, but I don't quite know how to make it fit well with this BV formalism. Mm-hmm. Because then in this integrating out things, one should also choose a Lagrangian sub-thing over which one integrates. And yeah, so I had some memory that we got a bit lost in that.
Mm-hmm. Okay, thank you.
But okay, but this is what happens for Chern-Simons and for this Poisson-Lie T-duality. But in principle, for any other example, when we just plug it into that machinery, it will spit out now a finite number of fields that live on sigma, and together with an action functional which is a solution of classical master equation. So we get somehow a thing in BV formalism. I don't know whether it answers the question. I said it was a picture. This was not a whatever, not math. Okay. Now, is it okay? I just told you shouldn't ask any questions right now, right? So are there any questions? Yeah, I was successful. Very good. Okay, so the moral here is that this at least AKSZ sandwich can be seen as this Lagrangian intersection story, and that one can compute with in various ways and get reasonably quick and nice results. But you wanted a down-to-earth things, so this is what's going to happen, and or probably underground things now, I should say. So we're going to do some calculations. The calculation is going to happen just for this. I recall there was this boundary condition for Chern-Simons theory. So we need to split G into this orthogonal sum of two subspaces. And then we want to consider, when sigma is the boundary of something, then we want to consider only those fields that are whose restriction not in this subcomplex. And you see this boundary condition, okay, now it's written in a classical way. It's just, I just told you what it is for a, what kind of condition it is for fields. It requires a conformal structure on sigma, just as it's written. But if we now try to perturbatively quantize this thing, so if we just really try to write down some perturbative expansion of Chern-Simons on something with this boundary condition, then who knows, maybe this will develop some anomaly that it will now depend more, not just on conformal structure, but really on some Riemannian metric with it, which is on sigma. That happens often, such a thing. And then we might need to renormalize things. The only thing to renormalize here is this splitting. So it's this subspace V plus, how it sits inside of G. And we would get some renormalization, group flow, and things like that. And yes, this is what happens. So let's go for it. And for some time, it would be good to keep in mind that, you know, this V plus and V minus and all this looks kind of complicated. So it's good to start with some simplified picture when this G is one-dimensional and everything is V plus and nothing is V minus when we have just this kind of splitting. And okay, sorry. So what we're going to consider, sorry, it's written here. So our three manifold is going to be a ball, three-dimensional ball. Its boundary is a sphere, so which we just identified with CP1. And we want to somehow find the perturbative way of calculating this Chern-Simons thingy with this boundary condition, or let's say with that boundary condition in a simple case. And now we know the rules of BB quantization. In principle, they say, yeah, we should choose a nice Lagrangian submanifold in the space of fields, so that now our action functional becomes kind of non-degenerate, so that we can actually invert the kinetic term and do such things. But in the end, the only thing that matters, at least if this Lagrangian submanifold is just a vector subspace, the only thing that matters is that we should find a propagator. So this is what we're going to do. So what do I mean by propagator? What it boils down to? So let us take the space of fields that satisfy the boundary condition. I mark it noted with this little b here. So it's the space of fields that, when restricted to CP1, they live in here, the space of forms. And the propagator in the end is going to be just a contracting homotopy for this complex. This complex is fortunately acyclic, so it's good, so such a thing will exist. So it should be H which satisfies this thingy. And it should be given by some nice integral kernel. So there should be some nice closed two form on the configuration space of 2 points in the three-dimensional ball, which implements H that satisfies that. And yeah, such a thing exists, and there is a very nice formula for that. There is a SL2C invariant P0 that one can find. So how does it work? Let me present you the formula in its glory. So what we need to do, so let's start with a point in here that means a pair of points in B3, like P1 and P2. So we simply connect them with the hyperbolic geodesic passing through these 2 points. And this geodesic now will end at two points on the boundary sphere on this S2 or CP1, which I call Z1 and Z2. And then our propagator is simply just 1 over 2 pi I and times this nice expression times this omega. So dz1, well, it's dz2 divided by z1 minus z2 squared. Now an exercise for you. Find a geometric meaning for this two form that doesn't use any, so doesn't use coordinates, doesn't use this coordinates z1, z2, and thus just discovered directly that it is PSL2C invariant. Okay, so you can stop listening to me and just start solving this exercise. Okay, but now you should be done. It's an easy exercise. Sorry.
What's the R? What's R?
You mean this thing? Oh,
yeah.
Sorry.
Well, the one. That's where it. Yeah. Okay. Thank you. Yeah, I didn't see that first.
Yeah. Sorry, I should probably say everything that's written on the slides. I'm doing this, so bad thing. Yeah. Yeah, R is the map that sends P1 and P2 to those endpoints Z1 and Z2, and then we just take this 1/2 pi I times R star of omega. Okay, that's the propagator. It's the propagator for this. Sorry for moving so much. I shouldn't be doing that. For this easy case when there is no Lie algebra here and we have just that thing. But okay, let me scroll slowly back there. But when we actually do have a Lie algebra split into those two subspaces, then the propagator is not much different. So simply for this V plus part, we would take the thing that we found here, this P0, and for V minus part, we would take P0 bar. So more precisely, our propagator, it's a two form with values in G tensor G. And yeah, as you see, we take P0 tensor the inner product on V plus. So that's this thing, this T plus, and plus P0 bar tensor the inner product on V minus. So that's in the end the propagator. And as I promised you or warned you, there would be now those Feynman integrals are going to diverge. Normally for Chern-Simons, such things shouldn't happen, but we will get divergences at the boundary. So the boundary condition is the bad thing. So inside there are no divergences, but when things come to the boundary, they might diverge. To deal with that, one needs to introduce a cutoff. And so what is this cutoff thingy? Basically, we simply, whenever those 2 points, this Z1 and Z2, so they were here, Z1 and Z2, when they are too close, then we declare that the thing is equal to 0. So we multiplied with this sharp cutoff, which is equal to 1 when those 2 points, Z1 and Z2, are reasonably far apart, but when they are closer than some prescribed L, then we say that it is 0. It's a very stupid cutoff, but it works here. So when as is written here. Now this L can also be a function, so on the sphere. So we can, this distance, this allowed distance might be different at different points. Or if you wish, you can think of this L as a particular choice of a Riemannian metric on the sphere in the given conformal class. That's another way how to think of it. Okay, so now Feynman diagrams. So in Chern-Simons theory, Feynman diagrams are given by trivalent graphs, possibly with some leaves, and we would put some sources or some external fields on those leaves. And so what does one do there? So to every vertex, as usually would put just the structure constants in G. On every edge, one puts this propagator. That's a thing that has values in G tensor G. And now we contract those G's with G stars, so somehow contracted each vertex, and in the end we integrate those forms by simply over all possible positions of those vertices. So those vertices will be located in our ball, and we take this integration. But since our propagator is really sum of two parts, it was probably written here, right? The propagator is like P0 tensor, the inner product on V plus, and P0 bar times the inner product on V minus. It is quite convenient to remember that, to write it as a sum. And now So right, each such a diagram has sum over all possible kind of signed diagrams where we're putting either P plus or P minus on those edges. So there are those signs that indicate which of them we put there. And the advantage of this splitting is that now this kind of signed diagram is computed as product of two things. So one thing is purely an integral, where you would see only those P0s or P0 bars. And the other thing is the same diagram, but now understood in the Lie algebra. So where you just see those structure constants of the Lie algebra at each vertex, and then orthogonal projections to either V plus or V minus at each edge. Okay, and it turns out that out of all these diagrams, when you just as usual in these third party kind of things, when we take just one particle irreducible diagrams, and when we stay with one loop diagrams, because that's the easiest thing to do, it turns out there is only one divergent diagram. So only one thing that where we need to introduce that cutoff to make that integral converge. It is this diagram, which is drawn here. Now, why is it true, this particular statement? So it's some kind of simple scaling argument that if there are more than two leaves, then those integrals will converge. So we can only have two external things. And now, say if we had say plus here, but also plus there, then the integral or the thing would be just identically zero, because it would be like P0 wedge P0, but P0 wedge P0 is equal to 0. So we really need to have plus and minus here. And it's slightly less obvious, but it's also not difficult to see that we also need to have plus and minus there. And there is this wonderful result that, which is equivalent basically to the divergence of this one diagram. That if you now try to take the limit when the cutoff goes to 0, so there is some physicsy writing here that we take the effective action, so the thing which is given by all those one particle irreducible diagrams, only to one loop, and with some particular cutoff L1, which we try to scale to 0. So we take it epsilon times the thing and take the limit epsilon goes to 0. We take it with some other cutoff. The outcome will be that, yeah, it now depends on how precisely we choose those cutoffs. There is this thing like logarithm of ratio of those L1 and L2. And now what's written here, you see this integral only over the boundary. Here we take our form A just on the boundary. Now we're staying on the boundary. This is its V plus part, that is V minus part. And then we contract those Lie algebra thingies using the diagram. So this is somehow, this diagram is now understood purely in Lie algebra. So A plus has values in V plus, A minus has values in V minus. We apply here the structure constants, and do it. And this can be understood. It is really the one loop Weil anomaly of our boundary condition. You see that this is how it actually depends on that L1 or on L2. So if this thing understood as a Lie diagram is equal to 0, then at least for one loop level, our thing has this Weil symmetry that just means that the boundary condition depends really only on the conformal structure and doesn't require any L1 or L2. But if it's not 0, that unfortunately, yeah, it's not conformal in that case. And to finish this story, using that result is Weil anomaly, we can now find this promised renormalization group flow of V plus as a subspace of G. So what is the idea anyway? So you see those diagrams are now, or those integrals are divergent. So we can put there's this kind of epsilon and try to take the limit and it will diverge. So the idea is to make also V plus epsilon dependent. That's the standard thing to do. And we want to design it in such a thing that this limit of those integrals, that it actually exists when epsilon goes to 0. Technically speaking, what we really want is that the limit of this derivative, that it's equal to 0. And also there is this one little technical thing that since we're in this BV picture, it doesn't really have to be 0. It's enough when it's BV exact. So BV exact things are somehow equivalent to 0. And so when we plug it in, that means that when we just differentiate things, for that one just takes this formula basically, and so where we can differentiate by epsilon. If you want to have that thing, we will get that this derivative of V plus. So that's how V plus flows. So one should understand that you have this V plus inside of G, and it will move by some linear map that goes from V plus to V minus. That's like infinitesimal deformation. And this infinitesimal deformation can then be computed, that it's some coefficient, and times, again, this diagram, the one that we saw in this Weil anomaly, understood just as the Lie diagram. So it's a map going from V plus to V minus. And this is at least for some people, it's a well-known story, this particular thing, which it is called the generalized Ricci tensor of our generalized metric. And to finish this off, so if we do the same calculations now, but in a Courant sigma model, again with boundary condition given by a generalized metric or something, then the same calculation will give us that this renormalization group flow is given now by the sum of these three diagrams. So what you're putting here, so we need to choose some trivialization of our Courant algebra as a vector bundle with a pairing. So then we have those structure, not constants, but functions appearing at vertices. And we also have the anchor maps. So that's what's happening here. And that's how a section of the Courant algebra becomes a vector field, and we differentiate those structure constants there, and the similar stuff here. So these are again just some one loop diagrams, and those one halves that one obtains when it computes those Feynman integrals. And it turns out this is again what is called the generalized Ricci tensor. And it is, in the case of an exact Courant algebra, it is simply equal to the ordinary Ricci tensor. So I can stop on this thing. Thanks a lot.
Thank you. Any brief questions or comments?
I'd like to ask a question. Yes, so this last one. So so what's different? What's different for Courant algebra is that there are these two new tadpole diagrams which are also divergent. Is that correct?
Yeah. Okay. They are not. Okay. I don't know whether technically it is tadpole or not, because there is this. There is this vertex, so there are already two propagators. Maybe.
Okay.
But yes, exactly as you said, there are two more divergent diagrams. There are these two, and then one needs to find those relative weights of how much they diverge. And it turns out this has like 1/2, this is minus 1/2 with respect to this diagram.
I see. Thank you.
Can I?
Yeah.
The renormalization flow equal to 0 is a requirement. Can we prove it? the equation renormalization flow equal to 0?
I'm not sure if I understand the question.
If I understand correctly, Noriaki is asking for fixed points of the flow.
Fixed points. Okay.
Yeah, fixed point is it is we can prove this equation, or this is the requirement of the theory.
It depends on. Yeah, as I said, I know nothing about physics. That's one thing, but then still, I can speak about it. It depends now. If you want it to be a conformal field theory, then this thing really has to be 0. It's not just for the renormalization group flow. The better thing to say is this Weil anomaly. So we want this thing to be independent of that cutoff in the limit when the cutoff shrinks. So
I see.
So to get a just one loop, it's only one loop calculation. Who knows what's going on for higher loops? So if you want that to be conformally invariant, so to depend only on the conformal structure, then this must be 0. And let's say I can, since this is just the result of a calculation, then one can say this is a result. So yeah, that's what one gets here. But if you're okay to have a something like a two-dimensional field theory which is not conformally invariant, then it seems to be like well defined. Just one is to allow this renormalization group flow. So then we don't need to impose that this diagram is equal to 0. I don't know whether it makes sense.
Hey, thank you.
Okay, thanks.
More questions?
A short question. I just didn't understand in between, and I realized too late to ask in between. But you said that basically the duality comes from changing the L. So you fix the F, the non-topological one, and you change the L. But how do you conclude that they're dual then? Or how is L and L prime related? Is there a relation between them?
Yeah, I don't conclude. I just declare them to be dual.
Okay, I see.
But there was this thing. Okay, let me go. I don't know. Do I still have some time? Okay, not too much, but let me still go there. There was this statement that if somehow we have two different things classically, but after quantization they become the same. Then this is what you would call, now this is probably a safe statement, that now they are dual in the sense that we have two descriptions of the same quantum field theory.
Okay.
And you see, this is what actually does happen for abelian Chern-Simons. So there is a, let's say, if you take the simplest, there we need to take a torus, that's our abelian group. And if you take the simplest one, then all those classical boundary conditions, they just coincide on the quantum level. If one takes something more complicated, then it's not true, but there are still only finitely many of those quantum boundary conditions, but infinitely general. Usually, the infinitely many of those classical boundary conditions, they are given by all possible Lagrangian subtori.
Okay, I see. Thank you.
There's some very nice paper by Kapustin and Saulina where they talk about that. So, but in more generally, this doesn't happen really. That things are classically different, and after quantization, they are the same. But let's say this is a super vague statement now, that it still does happen that things are classically very different, and after quantization they are not that different.
Okay.
It was okay. Not perfect. Okay.
No. I mean, like, just motivation is fine. I mean, that's you said it's a physics talk. That's fine. I was just wondering because, I mean, then in the next slide we're talking about the Lagrangian intersection and whether maybe there was some duality happening.
Okay, you see, maybe one thing that this becoming equal after quantization, that's a non-perturbative thing.
Yeah.
I mean, non-perturbative in the sense that h bar has to be a number. Even though say in abelian Chern-Simons, it's an easy thing, but still it's non-perturbative. So then all my perturbative nonsense cannot say anything about it.
Thank you.
Welcome.
May I follow up on this last question? What I'm looking at right now, so in the case of a non-abelian Chern-Simons, would the case when L1 and L2 are the two transverse Lagrangian subalgebras in the Mannian triple, would that be an example of this statement being true?
No, or at least let's say, I don't know. I don't know any single non-abelian example where this is true. It's okay. Let me say something wrong. Anyway, I was saying something wrong all the time, so it's fine, I guess. It would be true if if you take the corresponding quantum group, but now you have to take it with h bar equal to 1 or something, like h bar equal to a number. With this, so yeah. Let's suppose that we can do it. Then this thing would happen if the quantum group was actually trivial. I mean, if as an algebra if it was just C. It's a strange thing. Once you think of maybe like quantum groups at the root of unity or something of this sort, where things can become all of a sudden finite dimensional, and you don't ask. And for this abelian case, it somehow, yes, there it somehow exactly happens when you take those tori, which give you all this, yeah. At least that was my, let's say, coming from, this somehow is supposed to be related to Morita equivalence of non-commutative tori. And there exactly this thing is somehow happening. It's somewhere in the, people don't see it because they don't need it, but somewhere in the background, some Hopf algebra is trivial. And if you try to do this thing now in a non-abelian way, so for Poisson-Lie groups or for Poisson homogeneous spaces, then what one gets naively is that not quite Morita equivalent. There is some still Hopf algebra acting on things, and it will really become Morita equivalent only if that Hopf algebra was trivial. Yeah, it is not an answer, but at least it sounds cool.
Sure does. May I ask another question quickly?
Okay.
Brief one. A brief one.
Yes, yeah, very brief one. So what's so for the Courant sigma model? What's the analog of your coset theory that you get for bidimensional reduction?
Yeah, okay.
Well, the mod H, I mean.
Yeah, the thing. You see, maybe I was cheating a little bit. I said that we need to take a boundary conditions given by a DG Lagrangian submanifold somewhere, and for those Courant algebroids, to get something nice or meaningful, one needs to take a Lagrangian submanifold in this more whatever derived or something sense. So when the symplectic form doesn't really restrict to 0, but it restricts to something which is kind of Q exact or something like that.
So you don't get anything interesting just for a Dirac structure?
I don't understand what's happening for an ordinary Dirac structures in this sense. So what kind of things are happening there? It's a good question, and I should have prepared this answer for this talk, but somehow I forgot. And
well, maybe we could talk about this during the discussion.